So a very messy slide. My pen is still not working. I'm continuing to use my finger. But let's review what we did in the last lecture, the last two slides, where I make some mistake also at the last minute. What is the Schroedinger equation? Again, it is the equation, the governing equation, just like F equal to ma in classical Newtonian mechanics. It governs how the wave function evolve as a function of time, right? So in F equal to ma, it says that, for example, right, F equals to ma, right? It basically saying that, okay, you have something called acceleration, means the rates of change of the change of position, right? How does it change? It change depending on the force applied to it and the mass and its mass, right? And then we can solve everything. We know how the particle is going to move given the force and mass. And it's same here for Schroedinger equation. You have a wave function psi. The wave function characterizes the state of the system. And how does it change? It is the rate of change of the wave function, partial psi, partial t. Are you familiar with this? It means how it changes as a function of time, right? It's proportional to itself and also the Hamiltonian. And I said, what is a Hamiltonian? It is just the total energy of the system, which is kinetic energy plus potential energy, okay? And very often, it is written as T plus V. T is the kinetic energy and V is the potential energy, right? Am I right? Okay. And this is not surprising if someone tell you about that. Of course, the total energy of this system will determine how the wave function will evolve, right? In some sense, F equal to ma is also related to the energy of the system, right? So here we do not talk about the Lagrangian and Hamiltonian mechanics, which you learn in classical mechanics. We actually also describe the change of the system, any particle, using the Hamiltonian of the system, which we don't discuss here, right? We'll discuss in E274, but just take it for granted. That is the only thing I want you to memorize and be comfortable with, okay? Okay, so then what left is that if we trust this equation, right? You just trust it, don't question it. And then how do we use this equation? Now the psi, right, which is a wave function in the cat form. Of course, if it is 1 qubit, in a general representation is alpha 0 plus beta 1. Make sense, right? So alpha and beta, which has 4 degrees of freedom, characterize the state. It determines the state, right? And we can write it as alpha, beta. And of course, we know very well when we write this as a column, it means I have alpha part of 0 and I have beta part of 1. That is what we have been emphasizing since the beginning of the class. Don't mess up. Now, if this is the case, isn't that I can write partial psi, partial t as partial alpha, partial t, partial beta, partial t? Right? I just put in. Right? That is the meaning, right? Because that is the column. I have these two parameters. How the psi change really depends on how alpha and beta change, right? And so because of this, I write this equation as I h bar, partial alpha, partial t, partial beta, partial t equals to h alpha beta, because psi is just alpha beta. Now we changes to a matrix form, it becomes very easy. The so-called Schroedinger equation, if you learned that before, use the wave function approach, wave mechanics approach, it's very complicated. But when we are dealing with 1 qubit with 2 basis states, it is just a 2 by 2 matrix for the H, and it is just a 2 variable system of linear equation, like X and Y. You know how to solve it already. Okay. So our goal is to solve this equation. And then I try to say that, okay, Hamiltonian, we can look deeper. We don't need to memorize this, but we want to say that the Hamiltonian can be very general. It composes a part that is the energy relevant to each qubit if you have n qubit. And then you can also have the energy relevant to the interaction between the qubit. So you have Hij. Okay. What we want to look in this class is only the 1 qubit Hamiltonian, and basically it affects, like HI means it affects qubit I, right? So you usually just use the sigma, which is the Pauli matrix, as the Hamiltonian. That is easier to build physically. And then you will multiply it as an envelope that you determine how long it's going to turn it on. And by turning it on, then you will turn on the Hamiltonian. What does it mean? It basically means maybe you apply if you have let's say a qubit sitting in the vacuum, it doesn't do anything. So you can say the energy is zero, right? Because there's no energy, no potential energy, no kinetic energy. And now you shine a microwave pulse or a laser pulse to it, then you will interact with the EM field that you shine to it. Then it's going to evolve following this Schroedinger equation, right? So as a result, you only will shine this pulse for a finite amount of time. Otherwise, you keep evolving, right? You determine how much time you want to shine, what is the pulse shape, pulse frequency, pulse phase, etc. Then to modify the qubit. That is the idea behind this. Any questions? Yeah. What is the Hamiltonian one? Hamiltonian, you mean what is this? Correct. So it depends how you represent it, right? So in this case, based on this, you see it is a matrix. If you use the wave mechanics, right, then it will be some differential operator. For example, momentum, right? If you go to the you don't need to learn this, right? But let me try to talk about this a little bit more. The total energy may be p squared divided by 2m, which is the kinetic energy, right? For example, for this kinetic energy, you are going to change the p, right? P, you are going to substitute is what is that? Actually, I forgot. Is it divergence of x? If it is one dimension, you will just substitute p as partial x if it is one dimension, and then I think is negative I h bar partial x. If I'm correct, then p squared becomes will become negative I negative h bar square, right? And then second derivative of this one divided by 2m. Oh, and I forgot whether we have a negative, right? Do you see what I mean? I accidentally erase it. I don't mean to erase it. Yeah. So this is the how you work with the if you use the wave mechanic, you will change it to an operator. But now, if we're using the matrix, right, the Heisenberg approach, then this is a matrix. Now let's take a look. What do I mean by matrix? Now, if I have 1 qubit, how many basis states do I have? 0 and 1, right? So psi equal to alpha 0 plus beta 1. Now, then I substitute into this equation. I just repeat what I said earlier. Partial psi, partial t equal to partial alpha, partial t, partial beta, partial t. Then I write this equation, I h bar. I just substitute this whole thing here. This is psi, partial t, plus h bar, h times psi, right? This is also psi. Is this clear? Okay. And then I make a mistake last time, right? Now I apply a basis state. So k can be 0 or 1. Okay, I just give a general state, apply to the left. I try to do an inner product. So K goes in, partial alpha, partial T is a scalar, so I can take it out. So it becomes K inner product with 0. Similar here, I have K inner products with 1. I apply this to the left-hand side. I should do the same thing to the right-hand side. So the mistake I made last time was what? I applied K. I should not take H out because H is a matrix. It's an operator. So it will be H, K, H, and then inner product with alpha 0 plus beta 1. Is this clear? Any questions? I have this, there should be no, this 9 should be gone. Any question? This is important. Make it clear because we learned this before, right? But everyone okay with this? Who is okay, please raise your hand. Who is not okay? Yeah, you really need to ask because you will see this in the exam maybe, right? Right? So I make the mistake last time. Last time I put the H out and then I do inner product K with 0. Right? I forgot that H is a matrix. Right? I cannot do that. Okay? Now then if I do that, then I do case by case. What if K equal to 0? Right? It's up to me. I decided to apply 0. Then K inner product with 0, 0 inner product with 0 is 1. So I keep the partial alpha, partial T term. 0 inner product with 1 is 0 because again we are dealing with the orthonormal basis, right? So 0 and 1 are orthogonal to each other, right? So the whole left-hand side becomes IH bar partial alpha, partial T. The right-hand side is what? I cannot simplify it. I can take alpha out, then I have 0H0 because now I assume K is 0, right? So KH0 becomes 0H0. And beta becomes 0H1. Not beta, sorry. This term becomes beta times 0H1. Okay? I know the writing is bad, and here I'm missing a strict 9 also. And similarly, when K equal 1, then this time 1, 0 is gone, 1, 1 stays. So I have a partial beta. Oh, you cannot see. So you have partial beta, partial T, right? And then on the right-hand side, everything is the same except instead of 0, I get 1 to them. Now, what is this? Is this a number or what? What is the whole thing? It's a number. Just ask yourself, this is a column vector. This is a matrix. This is a row vector, right? Basically, this will give you a number because this is a vector. Matrix multiply a vector, give you a vector. Vector inner product vector, which is a number. Yeah? So if I want to write it again, I can say this. I can actually say that H0, I call it H00. It's just a number, right? 0H1, I can call it H01. 1H0, I can call it H10. I need to evaluate it. And that is the difficulty in solving the equation. You need to evaluate this number. Once you know this number, the rest is just the system of linear equation, right? And I also have H11, right? Like this. Is that okay? Now, if I write it in this way, you realize that the two equations, right? These are the two equations. Equation 1, equation 2. I have two equations. Then, basically, I can rewrite equation 1 and equation 2 will become this. I h bar partial alpha partial t, I h bar partial beta partial t equals to h00, h01, h10, h11 on alpha beta. Whether you believe me or not doesn't matter. Let's just take a look. Let's take a look if this is true. For example, the first row. Look at the first row. The left-hand side is what? I h bar partial alpha partial t, right? I take the first row. What is the first row of the vector on the right? How do you find it? This one is a matrix. This is a vector. It will give me a vector. How do I evaluate the first element of this vector? Say again. Row times column. So what is that? H00 times alpha plus H01 times beta. What is H00 based on what we define here? It's just 0, 0. 01 is 01. 0, H, 0, alpha plus 0, H1, beta. Take a look. What was this first equation? 0H0 alpha, 0H1 beta, 0H0 alpha, 0H1 beta, right? So we did not do anything new. This is just equivalent to equation 1. What we are doing is just to show that we try to solve this. We do some mathematical trick and come up with two equations, which are equation 1 and 2, by using the inner product. This equation is equivalent to the this matrix multiplication. When you equate the first element, I h bar partial alpha partial t, you get what we got in the first equation. And if you try the second one, you will get the same thing for second equation. And basically what I'm trying to say is that answer your question you asked earlier. What is H? H is a matrix. The difficulty is how you evaluate the matrix. That is where you get the physics. What type of microwave pulse you apply to it. Here determine the physics. And now you may say, exactly how should I put H, right? I think that is your real question. Exactly how should I put H? No, you actually, sometimes you don't know how to put H unless you are given the equation. But experimentally, you want to find is 0H0. What is this inner product that you have from experiment? And that will give you the H, if this is a new theory, right? Okay, any questions? Yeah. H bar is the Planck's constant. Yeah, sorry, I did not mention that. Just a constant, okay? Yeah, I should have mentioned that, yeah. Okay, so with this, I don't expect you to memorize this or being able to derive, but I hope you will be able to use this equation when you are asked to, right? Including in the future. So for example, let's take a look as an example, right? Rotation, right, on the broad sphere. How can we correlate the Schroedinger equation to the rotation? Now, if I assume this is given, let H equals to negative Hz sigma z. Here, I assume that I give you the Hamiltonian already. I give you the matrix form already. And that is something we will look at it later in next class, how we come up with this Hamiltonian. I will show you that by applying the magnetic field, vertical constant magnetic field for a spin, you will get this Hamiltonian. Now, let's say you already get this Hamiltonian, right? Then what does it look like? Then you just go through the math. Now, this hz is just exactly this h that I mentioned. It's just a scalar. How long you turn it on, and also the amplitude, right? So here is only the amplitude, not how long. Okay, this is just the amplitude. So it's equal to negative hc. What is sigma z? Thank you. Right. So this whole thing become negative hc 0 0 hz. Do you see that? That is the Hamiltonian already. With this, I will be able to solve how the wave function is going to evolve. I think about this. For example, I give you a general wave function, alpha 0 plus beta 1. Okay? Then now we are going to use the, yeah. Not a general example. This is a particular example for H, because your H can be anything. H is a 2 by 2 matrix, right? Yeah. Oh, sorry, you say HC. HC, yes, just a general scalar. Yeah, just a number. Yes, it's general. So it related to the strength of your external field. Yes. Then let's go back to the equation we have learned earlier. Look at this. Maybe the best is to look at here, right? I h bar partial alpha partial t equal to this one, right? So I'm going to write it. I h bar partial alpha partial t equals to alpha, getting very difficult to read, alpha h00 plus beta h01. And now we know what is h00. What is h00? Yes, 0h0 for the bracket notation, but what is the exact value? We know already. Negative c, yeah. So it is negative alpha hc, right? How about h01? h01, row, column, 0. So this term is gone. Then it becomes a very simple differential equation, right? Then what do we get? We say partial alpha partial t equals to negative 1 over I h bar. I put hc here and then alpha. Is that okay? I just put I h bar to the bottom and I have negative hc alpha. Right? If you remember, if you don't, that is fine. I don't require to have this knowledge in this class. If you forgot, just Google partial x. If you have a solution, equation, partial what? How about partial f, partial x equals to, let's say, k x, right? Then what is the solution? No, kf, I'm sorry. Then f must be equal to exponential kt, kx, because we are not using t, right? Because if you substitute this guy to the left, partial f partial x give you k exponential kx, right? Which is kf, right? So if you forgot that, it's fine, right? Just trust me, this is the solution. Then And that is not general enough. I'm sorry. You still can have this initial condition, F naught, right, which is a constant. So, which I forgot to say. So this one gives us what? Alpha equals to, and let me emphasize, this alpha is not just a constant, it's a constant as a function of time. Alpha of t equals to alpha 0 at the beginning, exponential negative hz divided by I h bar t. Am I right? Sorry. HC should not have a cross. Good catch. Because HC is just a constant. Okay? Thank you. Okay, now? Let me rewrite it a little bit more to put the negative I on the top. Then it is exponential h again hz over h bar and then I on top, so it is positive. Okay, because negative 1 over I is I. Now this one will give me the change of alpha. Look at this. It tell me exactly what is the initial alpha, right? Because when t equals 0, alpha 0 equal to alpha t equals alpha 0, right? So that is the initial. When t equals 0, this equal to 1, right? So just want you to just emphasize, right? Alpha when t equal to 0 is just equal to alpha naught. That is just your initial state. Then you apply this Hamiltonian, it's going to change like this. So okay? Okay, good. How about beta? Here I'm not going to show it. I will just say similarly, just go through the math. You will find that beta of t, right, equals to beta 0. Everything should be the same because let's look at the equation one more time. They are the same. Alpha, partial t, partial beta, partial t, and then alpha, beta are all on the right-hand side. They just have different coefficient. And then if you look at the coefficient now, they are the same except this guy is negative of the other. So you just go through the math. You will find that this is just exponential negative I hc divided by h bar t. Right? So you compare to the solution before, it's the same except that we have negative sign here. Is that okay? Now, then we want to study what it means on a broad sphere. What does it mean, right? Now you know how the alpha change, how the beta change. So let's recall. Maybe I should go to the next page. Yeah, let's just go directly to the next page because right. Let's go to the next slide. Let's look at this. Recall. On the broad sphere, how do you represent a state? Yeah, psi equal to alpha 0 plus beta 1. We also represent it as cosine theta divided by 2e to the power. Let me use e to the power. I phi divided by 2 but negative 0 plus psi theta divided by 2e to the power I phi divided by 2 1. Remember this? Yeah? So we already talked about this before, right? This is the this was the state, right? This is how we represent it. Now, if the initial state, if this part is a, we can treat this part as alpha 0. Treat this part as beta 0, correct? That was its state at the initial time. Then after let me use purple. After applying the Hamiltonian H, what would it be? We just say that alpha 0 becomes alpha 0 times, look at here, exponential something t, right? Times exponential negative I, actually we don't have negative, I, H, no, bar, Hc divided by H bar T. Do you remember what we say again? The solution is alpha of T after a certain time when we apply the Hamiltonian is alpha 0 times this exponential term, right? So isn't that after applying the magnetic field or the external Hamiltonian, I should change alpha 0 to alpha 0 times exponential IHC divided by H bar omega H bar T. Any questions? This is important. Anyone? Any questions? Is this clear? Right, this whole thing is alpha T, by the way, right? I don't know if you can see green. This whole thing is alpha of T. Then, of course, after I apply the Hamiltonian for time equal to T, then alpha 0 becomes this, right? What happened to beta then? What happened to beta? Can someone tell me? It was beta 0. What happened? Same thing, means it's beta 0 exponential negative IHZ divided by H bar T. Because I just showed you that, I did not show you, but I told you that beta of T is equal to beta 0 times this whole term after I apply the external magnetic field, the Hamiltonian. Right? So this one becomes this, right? Then what is the meaning of this term to the original alpha 0? Yeah. Do you see that the cosine term is not changed? What it changed is the exponential term. Because alpha 0 was e to the power r negative I phi divided by 2. Now it becomes e to the power negative I phi divided by 2 times exponential IHC divided by H bar T. So I can group these two terms together. Similarly, I can group these two terms together. Right? Let's take a look what it means. So now the wave function becomes cosine theta divided by 2, nothing changed. And then exponential, I'm going to take this out, I, negative I, divided by 2, and then I had the phi at the beginning, right? I have the phi, negative I divided by 2. Now I want to group them together, so I'm going to take out the I, add a negative, and then I have the phi divided by 2. So this becomes minus 2hz divided by h bar t. For state 1, state 0. Right, let's take a look again. Here I had e to the power negative I phi divided by t. And after applying the Hamiltonian, I added this exponential term. So this whole term, the cosine term, is not changed. But this one, I can combine it. I take out negative I divided by 2. Right? So then, effectively, the phi, it becomes negative I divided by 2 times phi minus this term. Yeah? Similarly, which I won't go into detail, for the second term, sign is not changed, but then the other becomes I divided by 2 phi. You will get the same thing, hc divided by h bar t. For 1. Why? Because this is positive I phi 2. This is negative I hc divided by h bar. I'm going to take out I divided by 2. So I have phi minus 2hc divided by h bar t. These two are exactly the same. And now what is the meaning of this state on the broad sphere? It is still saying that I have a polar angle, theta. But the azimuthal angle changed from phi to minus 2h bar divided by 2hc divided by h bar t. Theta unchanged. Right? But phi becomes phi minus 2h bar hc divided by h bar t. And what is the meaning on the broad sphere that the theta does not change, but the phi is changing? What does it mean to the state on the broad sphere? Pick up a phase, or it just rotates parallel to the equator, which we call it precession. Okay, just imagine now you're on San Francisco. You just move along the, I think it's latitude, right? I don't know. Yeah, then you go to Europe. You just keep rotating there, and that is called Larmor precession. Okay, you get something called Larmor precession. And it has a rate. It's rotating a certain frequency, right? Because phi is changing. Partial phi, partial t equals to negative 2hz divided by h bar. This is the, right? And we only take the magnitude because it's rotating clockwise. That's why it's negative. It gives us something called Larmor precession frequency. It tells us how fast it rotates on the broad sphere. Let me see. So finally, what I want to say is this. If I set the time so that 2hz divided by h bar equals to pi times t equals to pi, right? Because now I'm the one who set up the Hamiltonian. What is hc? hc is the Hamiltonian I apply to it, right? So I have the control whether it's large or small. And I also have control on the time. When do I want to turn on the Hamiltonian? So I can change hc and t such that it equals to pi. What does it mean when it is pi? It rotates about the broad sphere z-axis by pi degree. And that is the z gate. Remember, the z gate change the phase of 1, right? If I can add a pi to it, because e to the power pi is -1. Then I implemented a Z gate. So here is to show you the easiest one, right? The basic. If I can apply a Hamiltonian corresponds to the poly Z matrix, I apply it for the right time and right strength, then I will be able to implement a Z gate. That's all I want to say. Make sense? Any questions? Now then, this is the first time, right? We connect the matrix to the Schroedinger equation, although the matrix is given. But assume we can construct that matrix, then you know how to implement a Z gate. It's no longer just a simple matrix that you use in the algorithm. Right? So now, as the next step, then I want to discuss how to implement a spin qubit Z gate. Okay? And with that, now we need to go to physics, right? Up to now, we still don't have physics except the so-called Schroedinger equation, but it's just an equation. We don't know the physics yet. Okay? Any questions so far? Good, right? And then now we will see how can I construct a Z gate. But before that, I assume we all have no knowledge on magnetic moment, etc. We will try to talk about some of the basics first. If you have a current going through the loop, just take it for granted, you will generate something called magnetic moment. Right, so here why it's so, maybe can be more, we can derive more fundamentally, but just assume for experimental, you observe that current going through a loop using your right hand rule, you get something called magnetic moment. What is magnetic moment? Not important for this class. Just take it for granted, right? Otherwise, you need to go to the electromagnetics theory. Is generate a magnetic moment. Yeah, but why magnetic moment is important because it's going to have interaction with the magnetic field to create the Hamiltonian, right? So, but anyway, if you have a current going through a loop, you will generate the so-called magnetic moment, mu. And it is a vector. And usually we write mu equals to I, the current, times A. Now, this may be a little bit surprising to you, but those who have taken EM, you know that A can be a vector, right? The area, just because of for the formalism, for the to make the math work, we can define an area as a vector, right? So you can have a certain direction. So in this case, I have the area maybe here, okay? And then here is going to generate the mu, right? And at the same time, it is also the direction of the area. You need to define the area first. Define its direction first. Whether pointing up is positive or pointing down is positive. Once you define, then you just go through the math. Here, what I'm doing is such that you will follow the equation. The magnetic moment equals to current times area. So you have a larger area, you have a larger magnetic moment. You have a larger current, you have a larger magnetic moment. These are completely classical. But why I want to show that, because I just want you to at least have something to lean on when later, when you see something that difficult to understand, right? Now, then I'm going to play with some math, a little bit boring, but here you see that what is area, right? I'm going to stop the vector notation to make things easy. So mu equal to I times A. And what is A? If I assume it is a circle, is pi r squared. Okay, this is just the A. And then now at the same time, I want to say is that what is the current? Current is due to what? Due to the movement of a charge, right? So what is current due to movement of charge? How do you find it? What is the definition of current? Anyone remember? Current density times area, that is correct, but I'm asking for just the definition of current. Charge passing through a cross section per unit time, right? So this is number of charge passing through a certain point per unit time. Is the time required? So if I have only one charge, right? If I only have one charge, assume. No, actually I just call it Q. I don't need to say one charge. So assume I have the Q that passing through, keep going around. Now don't think about current, think about a particle with a certain charge. Maybe I should say this. A particle with charge Q. Okay, I have a particle with charge Q. Keep surrounding, keep circulating. How long does it take to come back? Right, because you want to find out how much charge per unit time, right? Then I just need to divide the charge by the time that it circulates back, right? So if in a unit time it circulates 2 times, then it's charge divided by 0.5, right? So how much time it takes to circulate back, depending on R. Of course, depends on its velocity also, right? So this is equals to Q pi R. I just write it as it is. The delta T is equal to the time required to travel back is equal to the, what is that? Velocity distance divided by velocity. So it's 2 pi r divided by v. Is that okay? This is delta t. This is the time, right? 2 pi r is how fast you travel, divided by your speed. Then that is your time, right? So as a result, this is equal to pi is cancel, r is cancel. I get q R and then V, but it looks the same. Sorry for my writing. Become 2VR, 2RV divided by 2, right? QRV divided by 2. Is this okay? Right. However, there's something more fundamental in physics, right? Velocity is not what we want. What we want to see is the linear momentum or the angular momentum. Okay? So again, this is a review of physics. If you have a particle, right, circulating from R, from the origin, with a velocity v, just like what we are doing here, the angular momentum is called L. In this case, it's equal to m times r times v in scalar form. Now I just use scalar form because it is circulating in a circle, so I don't need to use vector form. They are all 90 degrees, right? In reality, it's r cross p, but R cross V, but I just use this one, right? So I get this one. So this is equation 1, this is equation 2. With this 2, then now we can find out the relationship. The magnetic moment mu equals to Q divided by 2, right, times RV. But RV is just equal to L divided by M. So let me rewrite it, becomes Q divided by 2mL. Okay, so this is the last thing we want. And what I'm going through this physics, actually not that important in this class, but if you don't know them well, it's good to take a look. But here is the main point. For a charge with angular momentum, it will have the corresponding magnetic moment. While when we are proving, we assume that it is in circle, but that is general. If you're not in a circle, if you have a certain angular momentum in an ellipse, then you should have a corresponding magnetic moment. Yeah. Which one, say again? M, oh, sorry, the mass. This is the mass. The mass of this particle. Yeah, it's because I did not emphasize well, the current is generated by a particle with charge, right? And that's why we get this delta T. Okay, so it's okay you forget everything here, but this is a background if you want to go deeper, right? The most important thing is a charged particle with angular momentum. That means it must be traveling, right? Will give you the corresponding magnetic moment. You will generate something called magnetic moment. Again, take it for granted. Okay? And their ratio, gamma equals to Q divided by 2m, is the so-called gyromagnetic ratio. Okay? So you give me the angular momentum, I can find the magnetic moment based on the gyromagnetic ratio. Different particles have, okay, this is classical one. I'll talk about another thing later. So you really imagine, you can see it because this is a classical one. A particle is circulating, has angular momentum, then it has magnetic moment. And the ratio is given by this gyromagnetic ratio. Okay, any question? And this should be easy to understand if you accept that it has magnetic moment, okay? This one skip because I have enough space. Why I say this because I want to explain what is spin. Spin, while the name sounds familiar, is not really a spin. Spin is not that I say the spin of electron doesn't mean the electron is spinning like the Earth, because the electron is a point charge. Okay? It doesn't have dimension. Spin is just a characteristic of a particle, just like the charge. You say electron has a charge of negative 1.6 times 10 to the power negative 19. That is its characteristic. Spin is also the characteristic of some elementary particle. If you heard about quark, right? Anyone heard about quark? They talk about different colors, right? Red, blue, green, I don't know what color. 3 colors, right? They are not color because you cannot see that. It just turned out that their property is similar to the color we understand, because when you add red, green, blue together, become white or something, I don't know. Yeah, there's some interaction. We call it color. But you do not expect you see the color. And this one for you, probably it's easy to understand because you know that for such as elementary particle, how come you have, there's no color, right? But spin is something that we usually refuse to give up our belief that it is spinning. But it is not. It's just some name. You can call it your name, any name. call it SJSU or whatever, right? As long as you have the correct math. This is the first point. But why would the scientists do something so confusing to call it spin? That is because it has the effect as if it has a spin, right? So I just told you that a charged particle that is circulating with angular momentum has magnetic moment. Same here. So spin, I need to say this is given. There is something called spin. It is just a quantum number, a characteristic of the particle. Just like the electron, you say that it's on the L shell, n equals 0, n equals 1, n equals 2. It's a characteristic of that number. But now even it exists by itself, it has this number. It has a quantum number equals to plus or minus 1/2. Okay, here when I say this, I'm talking about electron, spin half particle. Okay, let's just talk about electron. Some other particle has integral spin or a different number of spin, right? So here I'm only talking about electron. It has spin plus 1 minus 1/2. That's the characteristic. But just like, I don't know, right? Whatever, I cannot say that. But something you can have plus 1/2 plus half or negative half. That is the characteristic. That's it, right? Nothing to do with its spinning, okay? But interesting thing is, with this spin quantum number, it happens to have angular momentum, even though it is not moving like a classical particle, but it has an angular momentum. Which is equals to plus minus 1/2 h bar in the z direction if we try to measure it in the z direction. Okay? So the result is that for if you add a magnetic field in the z direction, the electron will have an angular momentum correspond to plus minus 1/2 h bar. This is given, trust me, right? And they get this first from experiment. You cannot derive this from Schroedinger equation. If you go to the relativistic version of Schroedinger equation, which is the Dirac equation, which combines the relativistic theory and the quantum mechanics theory, this will come out by itself. But here it's really completely just based on experiment. If you heard about this Stern-Gerard experiment, you will see that the silver particle is going to move in two splits under a magnetic field. That's why it has two different angular momentum, magnetic moment or whatever. But you trust it, okay? So now I just say you have the spin number. It's given characteristic. Corresponding, it has the angular momentum. And now if you know a particle has angular momentum, a charged particle has angular momentum, based on the classical one, you expect it has magnetic moment. Even it's not really spinning, but it has magnetic moment. Okay? So because of this, it has the spin magnetic moment. What is the size of the magnetic moment? Can you guess? Based on what we learned. It must be related to the gyromagnetic ratio of that particle with times the angular momentum. Okay? So this is again given, right? Now, but here is something very interesting. If you use classical, you expect this. You expect the angular momentum is going to be equal to E divided by 2m, where E is the charge of the electron, times the angular momentum, correct? With E equals to negative 1.6. Oh my God. times 10 to the power negative 19 coulomb, right? Classically, remember, I'm showing you here, we went through the classical derivation. Magnetic moment equal to Q divided by 2m times L. Isn't that I should expect U mu equal to E divided by 2m times S? But this is wrong. This is wrong. It turns out that mu is approximately equals to E divided by m times S. It's 2 times larger. Approximately 2 times larger for electron. Now, then why? Just because it's quantum mechanics. Okay? Of course, there's some theory to talk about that. So in reality, what is that? In reality, we'll write it as mu E equals to G times E divided by 2m times S. With G is something called G factor, which is approximately equal to negative 2.002. Think about this. If it is negative 2, you exactly cancel, right? Then you will get the equation I sent you. Classically, G equal to 1. Then you will go back to E divided by 2m times S. Right? I introduced this because you don't need to really understand, but you can apply to the homework. But this is a good thing you will see very often. For example, for proton, the G is completely different. Okay? And the G can change, I think, in the semiconductor also. When you consider the electron confinement, it's not a free electron anymore. Or the effective mass can change. Just for the sake of education, it's good to also understand that we can also write this as G mu B S divided by H bar, where mu B is something called the Born magneton, which is equals to, let me see, E H bar divided by 2m. This is the so-called Born magneton. And that is approximately the magnetic moment you can have for one single electron. So this is like the, how do you say, the minimal size of the magnetic moment you can have due to the spin. Okay, I know this is a little bit confusing, but you do need to use this equation in your homework. But it's just substitution, right? But even up to here is not important. If you really feel it's too difficult, it's fine. But the reason I'm doing this is just I want you to appreciate spin is not really something spinning. And the reason we call it spin is because, see, because of this spin quantum number, we can have this magnetic moment. And it's also related to its angular momentum through the gyromagnetic ratio, although the gyromagnetic ratio is not the same as the classical one. But the concept is exactly the same as the classical one. That's why it is called spin. Okay? Any questions? Okay. And okay, I'm saying so much. Actually, I don't need to, but I do this because I hope you have some foundation. But anyway, our goal is what? Our goal is that if you have magnetic moment, you will interact with the magnetic field. So if I have a magnetic field pointing down, for example, B0 C hat, negative, right? In the space, I point a magnetic field, north pole on the top, south pole at the bottom. Magnetic field pointing down. And then at the same time, I have the magnetic moment, right? If now you don't know what's magnetic moment, just think about what we did here. Maybe night you have where's that? Current, right? Charge particle moving, then you have the magnetic moment. And due to EM theory, they are going to interact. Now, but of course, what we are saying is not really a moving charge. We're talking about the spin. But now you understand spin is just a property. It's not moving. However, it has the magnetic moment because it has spin number. So then it has the angular momentum. Then it has the magnetic moment. And again, by physics, what is so special about magnetic moment? The Hamiltonian of this interaction equals to negative dot product of magnetic moment and the external magnetic field. This is the dot product. Now, can you tell me if it is, okay, maybe I say a little bit more, which is equals to negative B times mu, their magnitude, cosine theta, right? That is the meaning of dot product. Let's look at two cases. If they are parallel, let me do this. This is the magnetic field. This is the magnetic moment pointing down. What will be the energy when they are in the same direction? Is it positive or negative? Same direction. Look at this. When they're same direction, theta is 0, right? So is it positive or negative? Negative, because you have negative here. Negative, or if you're parallel dot product, right? Energy is less than 0. If the magnetic moment is anti-parallel, what happened to the energy? It's going to be positive, right? Do you prefer higher energy or lower energy in a physical system? We always go to lower energy, right? But just a ground state. But here, actually, I don't need to ask this question. It's irrelevant. So that's what I want to show you. This is the energy scale. And assume I have a magnetic field pointing down. Equals to negative B0 C hat. Okay? Now, if I don't have any energy, no, I don't have electric field. Whether your magnetic moment goes up or goes down, I have the same energy if you don't have external magnetic field. Make sense? But now I turn on the magnetic field pointing down. One of them will have a lower energy and one has a higher energy. Which one has a lower energy? Magnetic moment pointing up or magnetic moment pointing down? Which one has a lower energy? My magnetic field is pointing down. Yeah? The one that aligns with the magnetic field has a lower energy. And that anti-parallel to the magnetic field, that means if your magnetic moment is pointing up, you have a higher energy, right? And the separation is how much? B0 mu. This is the separation, right? Because one of them plus B mu, another minus B mu. Is this okay? Now is the confusing part I have not told you. Let's look at this equation. Magnetic moment is proportional to the angular momentum, but G is negative. So if magnetic moment points up, angular momentum must be pointing down. And when angular momentum pointing down, it means it is spin down, right? Because I have a positive spin number, then I get positive angular momentum. A negative spin number, I get negative angular momentum. For electron, and spin direction and the magnetic moment are opposite. Is this okay? Make sense? If you have a positive charge, for example here, this is easy to understand. If I have positive charge rotating, then the magnetic moment and the angular momentum are in the same direction. But if it is negative charge, angular momentum will be the same as before because angular momentum is due to the mass. But then the magnetic moment is going to be in the opposite direction because magnetic moment is due to the charge, right? So what I want to say here is lower energy will be the one that is spin up. Higher energy will be the one that is spin down. When you point the magnetic field down, spin up has a lower energy, spin down has a higher energy. And this is consistent with the broad sphere we have been using. We try to put the spin up as zero state, spin down as the excited state, and usually we go from top to bottom. So this is a confusing part that I had when I studied because I always don't know how to map it. So you need to be careful about mapping this spin up and spin down. If they use proton as spin as a qubit, then the story will change, right? Because the magnetic moment is going to be in the same direction as the spin if it is proton because it's positive charge.